Hey, the topic we're talking about today is infinite limits. That corresponds to section 2.5 in our textbook. So what we're looking at really is kind of what happens when x gets really big or really small. So positive infinity or negative infinity. As x approaches positive infinity or negative infinity. So as it gets very big or very negative. So as x approaches positive infinity or negative infinity, what you're going to find is a bit of a parallel between what you saw in pre-calculus algebra 2 and end behavior. Those really are limits as x approaches positive or negative infinity. As you go really far to the right, as you go really far to the left, x, does it go up? Or sorry, y, does it go up? Or does it go down? So we're looking at what happens to y as x gets infinitely large. So infinitely positively large or infinitely negatively large. Either one. Now note, it makes no sense to talk about approaching infinity from the right or the left. So you won't see those superscripts, okay? We'll use the positive and negative signs for the infinity values themselves. So infinity, negative infinity. So to the right, to the left. Where's that box? There it is. Alright, so for this kind of quadratic looking function, we are going to negative infinity. The limit of fx as x goes to negative infinity, so going to the left. As you go to the left, the function is going up. So again, kind of clarifying, as we go left. And as we go left, we're going up, so we say, now infinity technically is not a limit, it's not unique, but for one-handed limits, we'll say we're going up towards positive infinity. Example 10, again, going towards negative infinity. So that is again as we go left. And as we go left, we see we're going up. So while the limit technically does not exist, we can say it's going up, positive infinity. For that example also. Now here we have some more interesting graphs. So we're going to look both at going left and at going right. Alright, so as we go to the left, we see this kind of a sinusoidal wave going down, going up, going down, going up, and it just keeps doing that. It kind of never goes above 1, never goes below -1. So it's always bouncing between those two as it goes to the left. So we have what we call oscillating behavior. I just realized I'm kind of doing the negative infinity first. My bad. So to explicitly say that, we're looking at the negative infinity going to the left. So we can say does not exist. And you don't really need to give this reason unless they ask for it. But we're doing the notes, so let's include the reason. So when you're going back and looking at it, you have a reason. It's because of oscillating behavior. Nope, 2 L's. Kind of going up, going down, just bouncing between the same two values. So if it's always the same two values, everything in between those, well, what is the unique or single answer? There isn't one. So the limit does not exist. As we go to the right, we see the curve is going down, up, down, up, down, up. But we see the curve is diminishing as it goes to the right. It's going up less, going down less. So we can see if we look at those lines, as you go to the left, the top and bottom lines. On the right, those lines, they're kind of coming down, coming up. More importantly, they're converging, going towards each other. So if we keep tracing to the right, going up is going to get lower, going down is going to get higher, and eventually they're going to level out. And the behavior will be 0. Now, will the function ever be a truly horizontal line? It won't. But if you took it far enough, you could predict that it would be a straight horizontal line. So not about what it is, but what it's doing. As it goes to the right, it's getting smaller and smaller, approaching 0. So not is 0, but approaching 0. Example 11, look at this. As we go to the right, curve's going up, but it's kind of slowing down, it's flattening out. Looks like it's approaching 1. Now, will it ever get to 1? No. Very sad story. But it's going towards 1. That's the predictive behavior that we're observing. As you go to the left, it's going up towards negative 1. So a couple of examples here. It says use a graphing utility to find each limit. Now this test is primarily, or the majority of it, is non-calculator. So you want to have a good idea what functions look like, okay? As you go through the year, you want to get better at visualizing what a function looks like, knowing parent functions, transformations, basic shapes. But for the notes, at the beginning of the year, we'll use a graphing utility. So I already have this loaded in Desmos. I believe we're the limit as x approaches 0. So we can look at the graph at the 0 as x approaches 0. Looks like the y value is 2. And this is a really good illustration of limits. As you zoom in, looks like the graph is approaching 2, the y value. Now this is good because infinity, getting infinitesimally big or small, you never truly get there. So as you zoom in, we can always zoom in further and further. And then eventually you see the graph kind of freaks out, doesn't quite know what to do, because at 2 it does not exist. Sorry, at x equals 0, it does not exist. But if you zoom out a little, based upon the behavior, looks like 2. So again, not what the function is, but what the function is approaching. Looks like it's approaching 2. Again, sad story, the saddest story in mathematics. It'll never truly be 2. But if somehow x got to 0, we could safely predict y would then get to 2. But x will never get to 0, y will never get to 2. But if they did, that's what would happen. For example, 14, a piecewise function. So f of x is always 1 when x is not equal to 2. So we have a horizontal line. Kind of draw a good enough graph here. So f of x is always 1 except at 2. At 2, f of x is 0. So at 2, the function is 0. But limits are not about what the function is, it's about what the function is approaching. As you get closer and closer to 2, not as you are to, as you get closer and closer to 2. The limit, so I won't use an equals, I'll rewrite the limit of f of x. Now notice I don't write x equals 2, x arrow 2, x is approaching 2. It's going to be 1. This absolute value function in example 15, absolute value x over x. So almost anything divided by itself is 1. But with the absolute value, the numerator is always positive. So you could have a positive over a negative or a positive over a positive. So whether it's negative or positive, it's going to be 1. Pretty much everywhere except at x equals 0. Because of course you can divide by 0. So our limit, we have divergent behavior. Those two values, those two branches are not getting closer, they're not touching. So our overall limit does not exist. We're not approaching one unique number. For example, 16, I have a graph of that. It's kind of a mess, alright? So as we come in from the left, we see it goes down, then it comes up, then it kind of freaks out. It eventually recovers, goes down to -1, up to 1, then kind of flattens out and goes off towards x approaching infinity. But we have that kind of crazy behavior. So again, drawing a good enough graph, just kind of comes down and then does all kinds of craziness and comes out of it. Is that what it looked like? I don't think it... Yeah, it should have been. Do that again. So going down, crazy, 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 and... So now I'm done with... Yeah, that's better. Not great, but good enough. A good enough graph. So this we call oscillating behavior also. Because the graph is just kind of a big mess in there. It's kind of maxing out at 1. It's bottoming out at -1. And then in between, who knows? So this limit also does not exist or is undefined, okay? So 3 reasons why limits fail to exist. Let me move. There we go. So 3 reasons why limits fail to exist. Number 1, you're approaching a different number from the right of C than from the left of C. So that is something, haven't used green yet. Let's use green. Something like this. Where you're coming up, you're coming down, but they don't quite meet each other. So you have divergent behavior. Reason 2, f(x) increases and decreases without bound as is equal to z. So that is something like your parent rational function. We have those 2 branches, one's going down, one's going up, as you approach some x value c. Example 3, f(x) is oscillating between 2 fixed values. Now that can be your basic sine or cosine wave. You can also classify what we saw in example 16, kind of that craziness. You can classify that as oscillating behavior also.